When people first hear that deep learning has different model families, it can sound like a confusing catalog of acronyms instead of a set of sensible design choices. The reality is that most neural network families exist because different kinds of data have different kinds of structure, and a model that respects the structure learns more reliably. Images have locality, meaning nearby pixels relate to each other, and text and events have order, meaning what comes before can change what comes after. When you pick a model family that matches the structure of your data, you are not just chasing performance. You are reducing the chance the model learns the wrong shortcut. That matters in cloud security and cybersecurity because signals arrive in different forms, from screenshots and scanned documents to sequences of log events. And the safest model is often the one that fits the data shape without unnecessary complexity. The aim here is to recognize the main families, understand what each one assumes about the world, and learn how to choose the right approach for the job. Before we continue, a quick note. This audio course is a companion to our Course Companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A helpful starting point is to think of model families as opinions about how information should flow through the network. A basic feed-forward network treats input as a fixed set of numbers where order and location do not inherently matter unless you design features that encode them. That can be perfectly fine for tabular data, like counts, averages, and categorical indicators that summarize behavior in a time window. When you move into data types where location and order matter, you need architectures that build those assumptions into the model, because otherwise the network must waste capacity learning what you already know. In security analytics, this shows up quickly when you compare a set of summary features to a raw sequence of events. If your question is about whether an account is risky based on aggregate statistics, a feed-forward approach can work well. If your question is about whether a sequence looks like credential stuffing or lateral movement, order matters, and the architecture should respect that. Recognizing what structure is present is the first step toward choosing wisely. Convolutional neural network, CNN, models exist because many problems have strong local patterns that repeat across a space, and images are the classic example. A CNN uses convolutional filters that slide across an image and detect patterns like edges, corners, textures, or higher-level shapes, while sharing the same filter weights across locations. That weight sharing is important because it drastically reduces the number of parameters compared to treating every pixel connection independently, which makes learning more efficient and less prone to overfitting. Another key property is that CNN layers build a hierarchy, where early layers detect simple features and later layers combine them into more complex structures. In cloud security, you might see image-like data in unexpected places, such as visual inspection of dashboards, screenshots attached to tickets, or representations like heat maps of activity over time and resources. The point is not that you will always use images, but that when locality and repeating patterns matter, a CNN is designed to exploit that structure. The way a CNN learns locality has practical consequences for what it is good at and what it struggles with. Because filters look at small neighborhoods, a CNN is naturally strong at detecting whether a pattern exists and where it exists, even if the pattern moves slightly. That is helpful when the same visual indicator appears in different positions, or when a signal is spatially local in a structured grid representation. However, a pure CNN is not inherently built to track long-range relationships across an entire image or across long sequences unless you add design choices that expand the receptive field. Beginners often assume a CNN sees the whole image at once like a person does, but the model builds understanding through layered local processing, and long-range context must be accumulated. In security contexts, this matters if you create image-like encodings of behavior, because the model may detect local bursts of activity, while missing a subtle global pattern unless the architecture supports it. A safe takeaway is that CNN strength comes from local pattern detection and parameter efficiency, not from general intelligence. Recurrent neural network, RNN, models are designed around a different kind of structure, which is sequence and time. Instead of processing all inputs at once, and our RNN processes a sequence step by step and carries forward a hidden state that acts like a memory of what has happened so far. That memory is what allows an RNN to model how earlier events influence later predictions, which is crucial in tasks like language, event streams, and user sessions. In cybersecurity, many important patterns are sequential, such as repeated login failures followed by a success from a new location or a chain of process launches that indicates exploitation. An RNN can, in principle, learn that the meaning of a single event depends on what came before it, which is hard for a purely feed-forward model unless you handcraft sequence features. The reason this family exists is that order is not a detail, it is part of the meaning. When you choose an RNN, you are deciding that temporal context should be learned, not merely summarized. Even though our RNN models are conceptually elegant, beginners should understand the practical challenge that shaped the next generation of sequence models. Vanilla RNN training can struggle with long sequences because the gradient signals used to update earlier steps can become very small or very large as they are propagated backward through time. When gradients become too small, the model has trouble learning long-term dependencies, meaning it may focus on recent events and forget earlier context. When gradients become too large, training can become unstable and weights can change in ways that break learning. This is not just a technical curiosity, because in real event data, the important clue might occur far earlier than the final outcome. In cloud security, an attacker's initial access might happen long before data exfiltration is detected, and a model that cannot maintain long-range context may miss the connective tissue. Understanding this limitation helps you choose the right family rather than assuming all sequence models behave the same. It also sets up why gated models were created to preserve useful memory across longer spans. Long short-term memory, LSTM, models are a specific kind of recurrent architecture designed to handle long-range dependencies more reliably by using gates that control information flow. Instead of a single hidden state that is always overwritten, an LSTM maintains an internal cell state that can carry information forward with less distortion, while gates decide what to keep, what to forget, and what to expose to the next step. The practical result is that LSTM models can learn dependencies that span longer sequences than a simple RNN often can, making them useful when early context matters. Beginners sometimes imagine gates as if the model is consciously choosing what to remember, but it is better to think of gates as learned switches that regulate signal flow to keep training stable. In security analytics, an LSTM can be a fit when the behavior you care about is defined by a progression, such as a slow build-up of reconnaissance followed by privilege escalation. The key idea is that LSTM models exist because memory needs to be protected during learning. Choosing between CNN, RNN, and LSTM becomes much easier when you focus on the shape of the input and the dependency structure of the task rather than the popularity of the method. If your data has spatial locality or can be represented as a grid where nearby positions have meaningful relationships, a CNN is often a natural starting point. If your data is a sequence where order matters and the meaning of an event depends on earlier events, recurrent approaches become more appropriate. If the sequence dependencies span long intervals and you cannot compress them into short summaries without losing crucial meaning, LSTM-style memory mechanisms may help. A beginner pitfall is choosing a deep model family because it sounds advanced, then discovering the model is learning the wrong thing because it is not aligned with the data structure. A safer practice is to describe what makes the prediction hard and what kind of context is required, then map that to a family that was designed for that kind of context. That approach also helps you explain your choice to stakeholders in plain language. Another important selection idea is to distinguish between tasks where you need detection of local features versus tasks where you need accumulation of evidence over time. Image classification, object detection, and visual anomaly spotting often benefit from local feature detectors that can recognize repeated motifs, which aligns well with CNN assumptions. Session-level risk scoring, behavior modeling, and sequence classification often benefit from models that can incorporate the order and timing of events, which aligns with our RNN and LSTM assumptions. In cloud security, the same dataset can sometimes support both views, such as representing a user session as a timeline image or as a sequence of categorical events, and the representation you choose influences which family makes sense. Beginners sometimes treat model families as interchangeable, but they are not, because they distribute capacity differently. A CNN spends its capacity on learning local patterns efficiently, while an LSTM spends capacity on learning how context persists. Matching the spending to the task is what makes the model choice defensible. Capacity and overfitting risk also differ by family, and that should influence your choice in environments where data can be limited or labels can be noisy. A model that is more expressive can fit more complex relationships, but it can also fit accidental patterns tied to a specific dataset or logging configuration. In security, labels often reflect investigative outcomes and operational definitions that can shift, so a model can learn organization-specific artifacts rather than attacker behaviors. A CNN trained on image-like representations can overfit to visual formatting or layout quirks if those are correlated with labels. An RNN or LSTM trained on sequences can overfit to common workflow sequences that happen to co-occur with incidents in the training set, such as a particular ticketing process rather than the underlying malicious action. These risks do not mean the models are bad, but they mean you must control training and evaluation carefully and avoid overclaiming. A wise selection considers not only what the model can learn, but what it might accidentally learn if given the chance. Training flow and evaluation expectations can also change depending on the family, because each family introduces different failure modes that you must watch for. With CNN models, a common issue is that the model may rely on superficial textures or artifacts rather than the deeper concept you intended, which can lead to surprising brittleness under small visual changes. With our RNN models, a common issue is that the model may focus too much on recent steps, acting as if it has short memory even when the task requires long context. With LSTM models, training can be more stable for long dependencies, but the model can still learn to ignore certain context if it is not consistently useful in training, which is why representation and labeling consistency matter. In security monitoring, data drift is a constant concern, and drift can present differently depending on the model family, such as new visual layouts and dashboards or new sequences of events due to policy changes. Recognizing these family-specific vulnerabilities helps you build monitoring and stakeholder messaging that fit reality. Safe practice means you describe not only what the model can do, but how it might fail. It is also valuable to recognize that real solutions often combine ideas rather than using a single family in isolation, especially when data has multiple modalities. A security case might include text from an alert description, numeric features summarizing behavior, and a sequence of events describing what happened, and each modality has different structure. Even if you are not building complex systems as a beginner, you should understand the principle that the architecture should respect the structure of each input type. A feed-forward component can handle stable numeric summaries, a recurrent component can handle ordered events, and a convolutional component can handle spatial encodings, with their outputs combined into a final decision layer. The main conceptual lesson is that model families are tools for representing structure, not badges of sophistication. In cloud security work, the right architecture is often the one that uses the simplest effective tool for each part of the problem, while keeping the overall behavior understandable and monitorable. When you can explain that reasoning, you show maturity beyond memorizing model names. To fit the right use case, you also need to think about what the output must be used for, because operational constraints often matter as much as raw predictive power. If the model will support real-time alerting, you may need consistent, stable behavior and predictable performance, which can influence how complex a sequence model you can justify. If the model will support batch analysis, you may tolerate heavier computation in exchange for better ranking of cases for investigation. If stakeholders require explanations for decisions, you may choose a model family that is easier to summarize or pair the model with explanation techniques, while still being honest about limits. In security contexts, false positives can create operational pain and false negatives can create risk exposure, so you must align the model family and thresholding strategy with the cost structure of mistakes. A beginner misunderstanding is treating architecture choice as a purely technical preference, when it is also a product and governance choice. Matching the model family to the decision context is what makes the system usable. Bringing everything together, Recognizing deep model families is less about memorizing acronyms and more about learning to see structure in data and selecting an architecture that matches that structure. CNN models are designed to learn local, repeating patterns efficiently, which makes them natural for image-like data and spatial representations where nearby relationships matter. RNN models are designed to learn from sequences by carrying state forward, which makes them useful when order and context shape meaning. LSTM models extend that idea by protecting long-range memory through gating, which makes them a stronger choice when important dependencies span longer intervals. Choosing the right family means considering data shape, dependency length, label quality, drift risk, and how the output will be used in cloud security decisions. When you can explain those connections clearly, you are demonstrating the core skill the CompTIA Data AI certification looks for, which is not just building models, but choosing them responsibly and predicting how they will behave in the real world.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.